So is anybody sleeping? Everybody fresh? Good. Any question? Why we are understanding these maybe boring things? Because we want to understand how to propose different models, and we want to understand what is happening underlying. If we don't understand, we just import library and run neural network, deep learning, then it works. We just change the parameters, then that trains your data. But as machine learning researchers, as developers, we want to see how we evaluate, how we can design model from scratch, how we can propose new models. And if you want to do that, you should know this, right? Impossible if you don't know this. It's like you want to build a car, you don't know how engine works. How to see engine is good or bad. You don't know how to evaluate the, like, this engine can work for years or 1 minute later it's gonna die. So you must know. So this is the reason that we are discussing this. Let's continue. After clarifying this, you will see that when we are going to more complex models, you will easily understand. You will see, oh, everything is more clear now. I know what's happened. Now we want to talk about multiple regression and multivariate multiple regression. So let's first define what is the multiple linear regression, then even make it a little bit more challenging with adding multivariate multiple regression in this chapter. So what we are going to cover, we will first introduce multiple linear regression, then most importantly we talk about feature selection. This feature selection and the techniques that we are going to talk about today are very important, not only here, like the deep learning most advanced technique that you have, you should know how to choose the features. So that we will see what are the techniques and how we can use these techniques. We have qualitative and quantitative independent variables discussions. What does it mean? It means that, so sometimes we have like gender, how you can use it for prediction. We are always talking about these lines over here, right? But how you can use gender to predict something. So we will see today if we have those kind of variables. We will talk about interaction between independent variables. We will see that, okay, variables can interact with each other and what kind of challenges are they bring to the model. And then finally, we will talk about multivariate multiple regression. So what was the linear regression? Today, because we've seen, no need to define it again, is a statistical model that shows the relationship between two variables, x and y, as you see in the, on the whiteboard. We assume linear relationship between variables. It means that like it's linear with something increasing, something else is increasing too. Why we are considering that? Because of simplicity and be able to understand the underlying concept. But later we want to release it also. So find the best fit line for data that we have, make prediction of the y by given x, and we discussed it a lot, that y hat is equal to intercept and the slope of the x. So we can write simple value over here. Like if this is the x, 1, 2, 3, 4, 5, 6, and etc. If this is like exactly in diagonal, I can write like y hat is equal to, for example, 5 added by, I write something based on random y, 2 times of the x. Then this gives me a line that with this line, with this equation, then I can predict something. This is the simplest one. Now, we want to define multiple linear regression. We say it is a statistical model that analyzes the relationship between a dependent variable and 2 or more independent variables. So here, I'm writing 1x over here on the plot, right? But what if I have the third dimension? What if I have 4, 5, 6th dimension? So that we call it simply as multiple linear regression. And we want to define it a little bit more in detail and see what are the challenges that we have. Of course, it is extension of simple linear regression, and the goal is fit again the best data line for the whole data that I have, and I can rewrite the equation like this: y hat is equal to 1 intercept added by theta hat 1 predicted value that I want to put here, x1, predicted slope for theta 2 times x2, and up to the end, up to the dimension that I have as xp. So in many problems, we don't have dimension of 1, 2. We have dimension of 10, 100, 1000. So this is the equation that can indicate. And if you remember, these slopes we were talking, so this is intercept, and these slopes we were talking and defined it as coefficients. So whenever again I am referring to coefficient, it means that I'm indicating these values over here that we want to predict. Okay. So we say, okay, as I mentioned, coefficients represent changes in dependent variable for 1 unit increase in corresponding independent variable while holding other variables steady. So if I want to understand the, in 3 dimensions, for example, if I want to understand how much this is changing the y, I also keep the other variables that I have constant. Otherwise, you cannot evaluate it, right? Because if you change some, at the same time, if you change second, you cannot understand what happened in the y. So the assumption that we have for now, you should consider that all the discussion that we will have, if we change something, the others, we keep it steady. Okay? So it is widely used technique in machine learning and artificial intelligence to predict models, multiple linear regression, and it still has its place, and there are many applications that is still we are using and we can use. In robotics is very applicable. In simple prediction data, very applicable. You have simple problem that usually you have couple of variables. We can still use it, and it is very efficient. And if we want to talk about the advantage of the multiple linear regression, first of all, simplicity. You don't need to do very extraordinary thing. Interpretability, very easy to interpret and discuss it, what's happening that is this outcome is coming. And most importantly, computationally, it is efficient, that with the simplest, with lowest cost, you can run it based on the data that you have. So, but most important and hidden reason that we are discussing is to understand underlying concept of also complex models. So if you want to have look at different samples, stock market prediction, the customer behavior prediction, medical diagnosis, energy consumption prediction, environmental modeling, all of these can be used also as a multilinear regression. In some cases, it has been shown that simpler models may perform even better, as well as the complex models, or even better. It means that this is true that you may have a very complex deep learning model to evaluate data. Based on that problem, you have a simple linear regression or a nonlinear regression, simple regression model that if you evaluate and compare, you see that this one is working better. So a long time ago, one of my students proposed a model. I remember deep network model, but the problem was simple. I asked him to compare it with linear regression, and that was existing there. Whatever he was doing, linear regression was working better. So it's still based on problem that you have. You may simply can solve it with linear regression, and you can see this statement in different books that they declare, emphasize on it that you should check it out. But the challenge that we have, we say if two or more independent variables are highly correlated, it can cause problems and challenge in regression model. What does it mean? It means that, let me a little bit clean here. When we have challenge if x1 and x2 that we want to predict the y here, so for x1, x2, if they are quite related to each other, you change a little bit of the x, you increase the value of x2, x1 is also increasing or decreasing. Not only the y, but also they are changing each other. So in those cases, then we have challenge here. So that you may now think, okay, if this case is happening, we cannot use linear regression. Today we are going to answer it. We can use. The techniques that we have are trying to determine some features that are not doing this effect on each other. And they are saying that the concept is this. When you are changing this, directly change this, it means that already you can pick one of these to determine the model, not pick two of those. Because whatever you're changing here, also changing that one, you don't need to consider that one. Throw it out as input feature. That's kind of not 100%, kind of, but gives you redundant information. So before continuing, we need to discuss about some challenge, and we define it. First of all, we need to declare the multi-collinearity. In multi-collinearity, there are some situations that two or more independent variables are highly correlated. So this highly correlation is not this one exactly. Highly correlation doesn't mean that in definition of the multi-collinearity, it doesn't mean that changing this certainly changes that. It is showing that they are highly correlated, but not that strong. So that we say difficult to determine their individual effect on dependent variable and resulting unstable and unreliable estimation too, that we call it multi-collinearity. And this may also lead for incorrect conclusion about the relationship between data. So, as I mentioned, in multi-collinearity, high correlation between independent variables does not necessarily mean that change in one variable changes the other one. But on the other hand, we have claims of causality that says that exactly. The claims of causality says if you change one, change another directly. That can result in changing another directly. And it's different from multi-collinearity. In next models that we will discuss, I may say the problem is multi-collinearity. The problem is claims of causality. Then you should know what's happening in discussions that later we will have. So, can anybody say any example? For example, here, for these two samples of real environment, think about it. For example, you can consider You have a home and you want to talk about home size. Then you want to talk about the number of rooms in the home. If number of rooms is increasing, is it certainly increasing the square meter of the home? Maybe. It's not definitely, but most likely is increasing. Then that's multicollinearity between those two variables. So to estimating the price, then you consider number of rooms and the square meter of the home. So those are a little bit challenging over there, for example. What about claims of causality? This one you should say. Find two variables that if we increase one, definitely other will be increased too. That's simple. Too many examples. I can say like this is the chair right here. I'm pushing. Amount of force that I'm pushing increasing. The speed is increasing, right? For this problem, variable the force and the variable speed is completely dependent. And I increase it, it increases. I decrease it, decreases. For this specific example. In real life, so now you want to estimate. You want to estimate with parameter 1, the force, parameter 2, the speed, and predict where it's end up. So that has claims of causality, and say if you want to use linear regression, you can use one of these samples. That works already. If you consider speed, you can easily estimate, right, where it's going after like 1 second with constant speed, where it's going to end up. Clear? Well, your faces are like surprised. It is simple, right? Yes? Good. So, what we should consider, I think we have the samples also here. So what we should consider as ideal case, we want to choose independent variables that are as dependent as each other that is possible. Because we say, okay, how if we choose more independent variables, we can consider their effect on the output much more in depth. It is to ensure each variable unique contribution on the output. And if we want to have interpretation of the possibility of them, we can say by keeping all variables fixed, we can interpret one variable change on y. We just need to, if you say like, if we keep other fixed, this should exactly give me the output that I want, not change the other one as much as possible. So here I think we have the examples that I already mentioned to you, the house pricing for correlated inputs here. I'm not going to explain it again. That, for example, the square footage and number of bedrooms, and this can cause multilinearity and claims of the causality. And on the other hand, not claims of causality. On the other hand, for uncorrelated data, we can, for example, consider customer satisfaction. Actually, this sample maybe is a little bit hard to understand in Taiwan. Because we say, okay, the customer satisfaction in a restaurant with two variables, waiting time for queue and food quality. So there is a restaurant, and the food quality, whatever it is, if you wait 1 hour or 1 minute, will not change, right? So the restaurant is same, works for years there. If I come wait 2 hours to eat that food, or 1 minute, I will eat the same food. The quality is not changing, correct? But in Taiwan, I think people think that the queue is longer, the food is more delicious. I don't know. My friends from Taiwan, they told me like this. But here we say no, actually. It doesn't matter. So waiting 20 minutes and 5 minutes will not change how much delicious it is. But if you consider, maybe you consider how long does it take that food be prepared inside the kitchen, then that can be a little bit different. It's slowly cooking, maybe more delicious. So that's another definition you should consider. So I think you can have like 5 minutes rest, then we continue. Okay, everybody, let's continue. So now, first of all, we want to have a quick look. When we are considering multiple linear regression, the equation that we were writing already were based on single linear regression, single update, a single variable mostly. But if you want to update the calculation of the, for example, one sample residual sum of square, how it looks like, RSS we've written like in this form, yi subtracted by y hat of I. So what we can write here for y hat of I, the prediction, we can write theta hat 0, theta hat 1, xi underline 1, that this indicates first variable. So previously we had xi, but xi were indicating was indicating each one of the samples in the data set, but here we can now separate it to new variable. So this is a new independent variable and the slope of that. Second variable and the slope of that, and up to p. So consider this, that we need to update the when we are calculating the multiple linear regression, just simply the equation should be updated. But now, the most important question that is very important in machine learning also is that is y explained by all independent variables or only use subset of them, so that we have feature selection. Feature selection is quite important. You are solving, for example, data allocation in servers, load balancing in servers. You're solving complex problem or whatever it is. You need to select the features. You're solving image processing problem. Whatever you're solving with the model that you want to do prediction, then you should consider which one of the features are important to select as input, as like these parameters. Now we want to see how we can select those. Traditionally, what you do, you say, okay, I'm a smart guy and no problem, I know what's the important, and I put the variables over there. That's fine. But is it all? No. We have different techniques to make sure that the variables that you are using are exactly fine. So there are a couple of reasons. One reason is that if you are, as I mentioned many times, you are expert in one field. But as machine learning developer, you should be able to analyze any kind of data. And if you want to choose the variables yourself, you must exactly know what's the problem. You must exactly know what this variable means and how it's affecting the data. But if you have too many, then you cannot choose. And we should have feature selection techniques. So it's declining indicating the importance of the variables. For example, is not limited to regression models. In machine learning models, are also is critical. And as I explained, is identifying the relationship of the features with the predict in the output. Also, it is not limited, as I mentioned, is useful in machine learning techniques. So let's have a look what techniques we have. We have the common models as all subset. We have best subset. We have forward selection. We have backward selection. We have the technique that is univariate feature selection. We have embedded methods, and we have wrapper methods. So these are different techniques for feature selection. What is the whole objective? This objective is says which one of these are important. Which one of these I should choose for my model automatically without me as an expert saying what to define. So let's dive in one by one to see how they are working and how we can use them. So in all subset technique, as the name is indicating, we want to fit a regression model for every possible combination of the available independent variables, then select the best subset of variables. So it's kind of, we want to do the all combination, generate a model, and for all combination after we generated model, then we say, okay, which one of the combination is the best. If you have like 5 x's, these 2 x's, that 2 x's, that 2 x's, that 3, that 4, that 5, we evaluate all and choose the best one. Of course, that's clear. It's almost impossible. The problem is that computationally very expensive, unless the problem is small. You have like 5 variables, then you are not sure that which one to choose, then you can generate for all combination, the model, and then you can choose the best. And you certainly say this is the best one and best choice. In that case, you can do. But if your model is more complex, then you cannot do, then computationally expensive. And it suffers from overfitting also. You should be careful with that. Because I introduced metrics, right? And if your model fitting better, then your metrics are better. And if you choose this technique, then we'll try to minimize the error there and give you the best model. And when you're choosing all subset, you should be careful that if you're using all variables and doing prediction, you may be overfitting already. So the challenge over here is overfitting, that you should be considered to solve it and how you can solve it. For example, sampling techniques. You can sample the data and do, for example, k-fold technique to fold it to different classes and train it on it. Second technique is best subset. Looks like, the name looks like confusion with the first one, but that's different. We say the objective is to evaluate a small number of promising subset based on some criteria that we are not there considering every possible subset. So how we can do that? We have to use some heuristics. Who knows what's the heuristic? No one passed artificial intelligence course or something? No one knows heuristic? Okay. I usually, when use some terms, I try to declare in the slides also that you understand. So heuristics is like search technique that quickly wants to find the optimal answer for you. So you write some technique, search technique. For example, one subset is greedy techniques. You know greedy techniques. You want to write some search to find the best answer to solve the problem. The robot is from here. Want to go to the corner over there. The greedy technique, search all possibilities and try to find the best one. That's greedy technique. Why we don't use greedy techniques in most of problems? Because the possibilities are too high and it takes forever to check all. Because of that, we also have class of heuristic techniques in artificial intelligence that search the algorithm. Here I've written for you the heuristic definition. For example, we have binary search, digester algorithm, then a couple of more algorithms that are in class of heuristic. So it means that for best subset selection, we are trying to use some simple search technique, for example, binary technique, in order to determine how to choose the best subset. What's the problem of this technique, best subset? Again, computational complexity. Again, overfitting problem. We may have missing variables problem. What's the missing variables problem? It means that maybe this heuristic that I've written maybe is not good heuristic and is like considering every time dropping some good valuable input for me. So it depends on, so missing variable depends on the level of heuristic algorithm that I defined over there. Any question? Is it clear? And also we have a multicollinearity problem here. Now you know what is it. For heuristic, also you need to know that in machine learning we discuss it a lot. In artificial intelligence course we discuss it a lot. If you are interested in, have a look. Heuristic techniques are, for example, you are playing games, right? In most of the games we have heuristics. The algorithms of game developers, I can say over 95% of the algorithms that you are interacting playing games, any kind of game, they are using heuristics. They are interacting with you. You're doing something, something is happening. You're path planning. You have a strategic game. You choose the agent and say from here go there. How path planning is happening. Most of them are heuristic, not machine learning techniques. They are heuristics. How they are efficient, how they are working, you can study if you are interested. And of course, you should be you should be interested and study. So, okay. The third technique that we have for feature selection is an invariate feature selection technique that says we want to select the most significant features based on individual statistical significance of each feature that we have. What does it mean? It means that, so make it a little bit more simpler here. So individually I want to say how much this affects the independent variable effects dependent, how much? I have metrics, right? And how much this one is affecting. Then I can say, I can choose the most significant ones. So, so this technique is simple and computationally efficient because you don't need to construct whole model. You just need to evaluate each one of these. Then then you can choose the most significant one over there. What is the problem for this technique? It does not consider the interaction or correlation between features because you independently, instead of having a model that considers all features, then choosing, for example, best subset, here independently you say, okay, what's the relationship, each one of them, and then you don't consider if they are correlated to each other. So you gain something, you lose something, exactly happening here. One is that, second is like you may miss also important variables in this technique. Why? Why you may miss important variable? Why? No answer? It's very simple. Because maybe I have a feature that in combination with the other one works, indicates the output. Solely shows nothing. It's quite possible, and so you have a feature that directly is not affecting the output, but in conjunction or in using together with other variables shows the effect on the output. That's the reason if you use this technique, although it is it is computationally efficient, but you have that problem. Now you may think, oh, okay, how to consider that then? So if you use this technique, you have that challenge. Depending on your, as expert, so what's your difference with other students that who don't know about these topics is here that you know that, okay, if I have a problem, I have a data set, and if I want to do feature selection on that data set, I have different techniques. One of the techniques that is simple, I know, is this technique that says, okay, I don't consider the relationship between data. And if you have knowledge of that you know that the relationship between data are not too high, then you can this technique and works very good. So somebody doesn't know about this, wants to implement machine learning technique on the same data set, will try 100 times, you try 2 times. That's your difference with them. You easily can choose the approach. So you easily can say, okay, what should be the answer to quickly find the final result. So you may think, okay, when I'm training a model, I don't know, I have no idea. I'm changing the parameters. I don't know which model to choose. I don't know which approach to choose. Why you don't know? Because you don't know the concepts. When you know the concepts, then you see, okay, these are the parameters that I should consider, then the algorithm should be this. Or I should try these 2-3 algorithms. For sure, one of these will work better. So that's your difference with somebody that doesn't know, just knows coding. Very expert programmer, but doesn't know the underlying concepts, just playing with the parameters, randomly try to find base. Clear? Next technique is forward selection. In forward selection, what we do? We say we start with empty model. What can be empty model? Y hat I is equal to just intercept, theta hat 0. We don't have any slopes. When we don't have any slope, what does it mean? We are not considering x's, right? There is no x here. So none of these is affecting there, nothing. Then what we do? Sequentially adding the most significant variable to the model. Then I have like 100 of x's. Then I find the one, which one is the best one based on one independent variable significant. Then I add it to the model. For example, I write y hat I is equal to theta hat 0 that I had added by, for example, here x3. Theta 1 x3 I add to model. This is called forward selection and tries to bring one by one the most important feature into model. Bring one by one, bring one by one. Then how to detect significance of the variable? As I already explained to you, we said fit a simple linear regression model for each independent variable independently. Then we select the best one that has highest correlation, for example. Highest value for those intercept and the slope of that independent one. Like I choose this. I draw the model and evaluate it, then choose the best one and bring in forward selection similar to the previous. What are the problems of forward selection? Multicollinearity, computational complexity, overfitting may happen. So we have different approaches to prevent this. I already mentioned. Something new that may happen here is sequentially bias. Sequentially bias means that the order of adding variables maybe gives me something good or bad. A little bit complex to understand, but you need to think deep. So the order that you are adding the parameters into model can cause that you miss something else. For example, like you add from its forward selection, you add the best one, next best one, next best one, next best one. But if you If you didn't add the second best one and add something worse, maybe model was better. So the order of adding, like you add x1, x2, x5, x6. So let's say this is the best one, second best one, third best one. We say maybe if you didn't add this one and you add something like in 10th rank, x like 12, then this would work better. And that's challenge of forward selection solution for feature selection technique. We have similar technique called as backward elimination. The backward elimination does the same thing, but this time considers all and removes the worst one by one. And you think everything is repetitive. Here we say the model fitting the model, just we need to consider when to stop. Stopping is the when we, for example, consider the R square and put some threshold. Based on that R square threshold, we say that our model is not overfitting and is best one. And also can be expert judgment. You can say, okay, now this is good, it's enough, as expert to the value. What is the problem? The problems are exactly similar to forward selection. Just that one comes from considering all, considering null, then adding here, consider all and removing one by one the features. What you usually do as like expert, when you want to solve a problem, you think, consider some features. Then you see that your problem is not working. For example, you are doing image processing, you consider color detection for object detection. Then you think, oh, color is not enough, I need to also consider shape. You bring second feature. And you see, no, it's not working still. I need to also consider motion. That's third feature. As expert, you're bringing, right? But these techniques automatically does that for you and make sure that your problem can be solved. We have two more techniques. One is embedded methods. Embedded methods is kind of interesting. Says that meanwhile that you're training this, you also change the reward function somehow that at the same time feature selection is happening too. Who can say how? If somebody says how, I can give positive mark. Directly to the end mark. To the final mark that you have. Nobody? Hugo? PhD students should answer, at least. So we want to, for feature selection, we want to use embedded method. And we want to do the integration of the feature selection at the same time. How can I do it? I can write the same equation and put 0 here, for example. If I put 0 here, what happens? The effect of all this goes away, right? Then my objective function can consider also making them eliminate from the considering in the model, simply. So I can kind of either can add more variable here, or either consider the same one. It's common to use something here also, that you just bring the more effect or decrease it to 0, eliminate it from model. And at the same time, if you do that, not only you are finding this and finding which one to bring to the game or not bring. Meanwhile, you can train it, and this is called embedded. And this is like kind of very interesting model, right? If you can at the same, now consider, not in linear regression, consider you are doing complex deep learning model for complex problem. If you can do this, how interesting it can be. Now you can consider, okay, if we want to, this is research topic, if we want to bring this concept into reinforcement learning, deep reinforcement learning, to the reward function, to the feature selection of the agent that is interacting in the environment. These are hot, very top-level research topics that you can think about it. And like there, because we already say what are the action space, what are the state space, what are the everything, we could clarify. But if we bring the same concept and put it in that high-level thing, and at the same time also finding what is important. So these are kind of embedded methods that are interesting research area in machine learning. So one of the techniques also called regularization technique. Later we will discuss it. I'm not going to open it now much more in detail. So we can say we want to penalize the complexity of model and shrink the coefficient of the less important features, for example, as 0. What kind of techniques can do this for us? We are not limited. Also, we can use decision trees, random forest, L1 regularization. That these are techniques that we can use. There are many more. We haven't discussed these. As much as we have time, I will introduce them for you to see how they are working. Those are famous techniques. So embedded methods can select subset of features that are relevant while avoiding also overfitting because we can write objective function there for us. The problems is parameter tuning challenge. When you do that, how to tune the parameters to make decision is a little bit challenging, like many learning algorithms. And also non-robustness can happen because it is sensitive to, it can be sensitive to outlier. What is the outlier? Outlier means kind of noise. So it can be sensitive to noise, the data that is being measured, but they are wrong data. You're like, for example, you're asking the price of home in city. One of the agents is like, just feels something wrong. Put something randomly. The home is here X value. So you have dozens of data, that's outlier, some error that you have that is wrong. So that this problem can be effective based on that. You should consider it. Not it means that like if you have error cannot use this. No, you just need to be aware of it. And interpretability, it may produce a little bit more complex models that are not easy to interpret. You should take it into consideration. Next model that we are going to talk is wrapper methods. Wrapper methods are kind of, we say, let's use another specific machine learning technique to evaluate subsets of features. This is also very common. You can find too many publications. Just write on the Google Scholar, feature selection technique with, I don't know, the X algorithm, reinforcement learning, machine learning, different techniques, random forest, optimization techniques, tremendous amount of optimization techniques. For example, genetic algorithm, multi-objective genetic algorithms are specifically developed to solve this problem for feature selection. They are not intending to solve whole problem. They are intending to solve feature selection for that problem. For example, load balancing on the servers. So these are applications that are used for this, and we are trying to use another machine learning technique to find the features. Iteratively building models, and the basis, we choose different subset of features that we have, or independent variables, then perform the calculate the performance and see how it is working. Of course, it's clear that wrapper models can potentially lead to have the best result among the other ones, because other ones, for example, forward selection, we were just ranking and choosing the next best. In elimination, we were ranking and choosing, but this one is more flexible. Similar to embedded methods, we can use also another techniques, so same decision tree, random forest, support vector machine can be used. We will introduce these later, especially support vector machine, how it works. We can use it, but the purpose there is embedded, but here is not embedded anymore. Is separately construct a model and train to find the best one. But on the other hand, what are the challenges and problems? Computational complexity, that of course it takes time, and because of that is very expensive. So I think these two lines are almost the same. Yeah, just emphasizing that is more expensive than embedded methods. Embedded methods were expensive than the other ones, but computationally expensive. The wrapper models is a little bit higher than, not a little bit, almost higher than the embedded models. So, any questions so far? If no question, I want to change the topic now. Prepare your brains. Now we want to talk about, so I exemplified for you for gender. If one of these features is like gender, where are the markers? X1, X2. One of these features are like true, false, like education level. So how can I do? We call it as qualitative or categorical predictors that we should somehow bring it into the model to consider, right? We want to see today how we can bring it into linear regression, so that in other models also we can consider something similar. So to answer what if we have qualitative variables, for example, qualitative, as I mentioned, gender can be, education level can be, marital status can be, married, single, divorced, etc. Occupation can be, the region of the where a person is living, type of car can be, the brand of the phone can be, anything. So you are doing marketing, for example. You want to advertise some products. That what does social media is doing now. The advertisement on your phone is different from your friend's phone, based on the region that you live in. From country X, from the country Y is different. How these are happening? These are happening based on something similar topics that we are considering in qualitative variables. For example, gender can affect of course, the advertisement of the product. So we want to see how we can consider this and bring it into the equation. If we start with simple example, we say for credit card balance between male and females, how we can define it. The definition of the true-false values can be called also as dummy variables. And how we can do that, for dummy variable, we can say, okay, xi, the feature independent variables can be 0 and 1. For example, 0 is female, 1 is male. So this variable indicates gender for me, and how can I bring it into the model? I can rewrite the model in this form. I can say that, okay, the prediction, the model output, so it should have been hat, y hat of the I equal to the same regression model that I have, the intercept and the slope of the variable. But now I want to consider this 0 and 1 as male and female, so that I can rewrite the term in that form. If female, I have this term. If male, I have this term. What is happening? Just consider this 0 over here. 0 is xi, right? If you, for female, if we put 0 on the xi over here as x1 in this specific example, then this term will go away, right? Then I can write, if this goes away, I can write theta 0 added by the epsilon error that I have. Theta 0 added by epsilon. What if it's 1, then we have this term. The 1 times theta hat 1 becomes theta hat 0 added by theta hat 1 added by error. So what I did, I converted dummy variable or true-false variable to the regression model in this form. Very simple. Any question? Okay. So now, keep the same equation that we've defined. Now we can have a little bit of discussion. We can say this theta hat 0 is indicating average credit card balance for female, because we said if female, this equation, and we don't have anything related to male in this term, so that we can interpret theta hat 0 is showing me the average credit card balance for female. On the other hand, theta hat 1 over here can be indicating the differences in credit card balance between male and females. So this is interpretation, or how we can read based on what we've done and bring it to the regression model. So you may think, okay, instead of 0, 1, if it was 1, 0, what would happen? Nothing, just the same. These will be switched, then interpretation will be, for example, here for male, and here the same, again the differences. So that now we can estimate the coefficients, again, theta hat 0 and theta hat 1 to fit the linear model and predict the data. The same problem we solved. Just again find the theta hat 0, theta hat 1. But this time, what was the difference? The difference was that I have a qualitative variable. We have a couple of notes to be mentioned. We say, in this case, the sign of coefficient indicates something for me. The sign of coefficient, for example, this theta hat 1, can indicate the direction of relationship between gender and credit card. Think about it. What does it mean? It means that after I define the model like this, then I train the model. Based on that trained model, I have coefficient values, right? Theta hat, theta 0. Based on the value that I see there, I can understand something meaningful also. That one is the sign of the coefficients. For example, we say, if we see that theta hat 1 is positive, and not only positive, it is also statistically significant, How we could say that? If f is statistic p-value, we must also check those. If statistically significant, it means that there is relationship between input and output. First of all, that's first rule. If there is relationship, and if the theta hat 1 is positive, I can interpret it in this form. I can say we can conclude that the average, on average, males have higher credit card balance than females. So you collect lots of data from bank, from credit card accounts, and you want to just evaluate if male and female, how much money they have. And if you, after you do the model, and you see the theta hat 1 is positive, you can say, yeah, males have more money. Otherwise, you say female have more money. But of course, if it is meaningful, if it is statistically significant. Otherwise, the data that you collected based on the x that you have says it's not making sense. You cannot consider that. Okay, the same thing in vice versa. Female have higher credit card values. Now the question is, we have two questions. What if we find that theta hat 1 is negative or positive, but not significantly, statistically significant? I answered already that we can say we have not enough evidence to conclude that. To conclude that, we need more features from credit card, for example. Second question is then arise that does it mean that between two groups there is no significant? The answer can be, to evaluate that, we need to consider other parameters too. We cannot decide based on one, because maybe the information that we get is not sufficient. It is in case that we see that it is not significant statistically. How we could say that with p-value, t-statistics, and those parameters. Any question? Now, if you think, okay, we declare just one dummy variable. If you have two, for example, what we do? Or if we have higher level of the dummy variables. So if you have multiple dummy variables for each category, what we do, for example, another example, let's consider the college education, bachelor, master, PhD. So a person can be bachelor, master, PhD. We only consider, like in this sample, to have three students who entered the university. So what we can do, we can declare two variables. For first one, xi1, 1 is bachelor, 0 is not bachelor. So 1 and 0 is based on my definition, whatever it can be. 1, 0, a dummy variable. On the other hand, I can define x2, that is 1 for master, 0 is not master. So of course it's clear, if none of these happens, that person is PhD, right? Because there can be three options. So that if I have three levels over there, I can use 2, the level minus 1, then I can declare the features for that dummy variables and declare them. But here I stated that this 1, 2 again, indicating different x's. xi of the 1, xi of the 2. Clear? Same note. Now how we can consider it? How we can bring it into the linear regression model? If you have a look, here the same equation. This was like linear regression, right? Theta hat 0 added by theta hat 1 times xi1, theta hat 2 xi2, considering 2 added by epsilon. Instead of that, I can now, based on that 1, 0, 1, 0, again put them here. And if you put them here, 1, 0, 1, 0, then you can see that for PhD, we only have theta hat 0 added by epsilon. Because when this guy is PhD, is not master, is not bachelor, right? This 0, this 0. If you replace 0, 0, these terms go away, right? Then you have theta hat 0 added by epsilon. For master 1, 0, but this will be 0. Then we have the theta hat 0 added by theta 2 epsilon. For the bachelor, theta 1 epsilon. So what we write in regression model, we write y hat I equal to this term. Then I consider categorical data in my regression model so that I can do prediction now. Just finding the parameters of the theta 0, theta hat 0, theta hat 1, theta hat 2. So how we can interpret it? We say assuming 1 unit increase in xi1 while holding xi2 is constant. We can say if theta hat 1 for predicting predicting theta hat 1 for xi1 positive and statistically significant, it means that we can conclude that there is positive relationship between xi and xi1 and y. So if for theta hat 1 we consider xi1 over here, then it says that this theta hat 1, there is if there is positive relationship, then it is increasing. Increasing means that like here, it's also clear. You see, if 0 is decreasing, if 1 is increasing, right? And if you consider, for example, salary as y output, and for salary, for not bachelor, will be lower, for bachelor, it will be higher. With this interpretation and definition. For master, the same. If not master, will be lower, if master, will be higher. With 0, 1 categorical definitions. And we can interpret it also, simply. Clear? So you may say, okay, if we would switch this in definition, then of course, then the interpretation will be switched to, then the increase will be higher. You should a little bit dedicate time also to consider. Besides that, if you want to combine both qualitative and quantitative together now, you say, okay, we know that dummy variable true false how it's working, but what about we have already variables that they are like some values and they are quantitative. Then what we do, we can write example here. For example, I define the working hours and gender for indicating the income. So how much money you're earning based on your gender and working hours. We want to evaluate. We don't know how it's in the world. We don't discuss that. We just want to see how we can evaluate it. We can write it in this form. yi is equal to the output is equal to the intercept again. This term over here indicates the working hour, the same linear equation that I had. Here is dummy, gender, theta hat 2 and 0. So why 0? Because if I write this term as theta hat 1 xi1, if female put 0, this becomes 0, right? So that term is 0. And here I have theta hat 2 as second parameter, because if I put 1, so consider like we have theta hat 2 xi2. I put 1, then I don't need to write it. Here, because 0 becomes 0, then add it by epsilon error. So now I combined the qualitative and quantitative together, so that I can find the parameters for theta hat 1, theta hat 2. Then I can interpret that, okay, the working hours and gender is affecting on the income or not, based on samples that you have. So you have practice. I think I will stop here. Also, we don't have too much slides, but anyway, I think you should practice. You need to combine now qualitative and quantitative approaches together. So I gave you examples of this one already. And you need to now bring some example like gender, code it and add it, and try to evaluate the same p-value and t-statistics that already gave to you, and to see if it's statistically significant or not based on your result that you have. Clear? Any question? Now open the example that I gave you, add this part simply. Try to define a categorical variable and add it and interpret it. And there we saw how we can include it into model to have better predictions. So here the combination has been shown, and we have the interaction between variables. So now we want to talk about, okay, before this slide, when we were talking, we were considering that each one of the x's in each one of the inputs, or each one of the independent variables, separately are affecting or changing the output y, not together. Because in the equation that we were defining, we were considering they are separately affecting the output, the dependent variable. But now we want to say, okay, what if we have interaction between variables? So we say, okay, as I mentioned, mostly we assume the effects are independent, but actually they are not. If you have a look at this equation, the output is equal to the intercept added by the slope of the each one of the variables that we have. So if we have the xi1 and xi2 as two features or two independent variables that are affecting the dependent variable that we have, they consider separately. So now it means that this theta hat 1 only changed this variable x's, and this theta hat 2 only effective based on the separate feature that we considered. So I'm using these three terms in together when I call features, when I call input, when I call independent variable. All I mean the x's. So far, you know. Now here we have an example to make it more clear. Let's say we have example of the advertisement on social media. So let's consider the xi1 first feature as social media advertisement. How many hours, for example, we advertise you, or how much money we advertise on social media. xi2 as advertisement on TV, and yi is sale, the output as sale. So now by this equation, as I mentioned, we are not considering the interactions. So what we can do, we can say that, okay, let's assume spending money on social media increases the effectiveness of the advertising on TV. So I'm a customer. When I see advertisement on both TV and social media, I'm more likely to buy something than just only seeing on TV or just only seeing on social media. For example, if I see only on social media, I may don't trust it. But if I see in both TV and social media, maybe I'm more attracted to buy it. So this is the concept of interaction. So when you collect data from previous sales that you have, some products only advertise on TV, some only advertise on social media, some on both. So based on this sample, we know that there should be some interaction. So we can say based on that, in social media, we have a higher impact on what we can solely sell to get maximum reward. It means that so if we only advertise in one media, we cannot get maximum of that sale. And we can consider, okay, maybe if we spend 50% on social media and 50% on TV, finally we get maybe higher sale than only advertising in one of them. That is the same concept. So to prove that, we can have a look at this plot. So let's consider these are advertisements on social media and TV. So when we are advertising on both these cases, you can see that the amount of sale is maximum. But when we are only advertising on one of the medias, if we like these cases mostly advertised on, for example, TV, right? Most of the money go to TV, or all of the money go to TV. The amount of profit, amount of sale is over here. On the social media, amount of profit is here. But when it's both, gets higher. So interaction between, so far should be very clear that interaction between variables is very important to be considered. Now, we want to say, okay, how we can consider that interaction in our term equation. What we need to do, that's not very complex, very simple. So we write the same term, dy, theta hat 0, theta hat 1, xi1, and theta 2, xi2. So far we've seen up to here. So we want to find the intercept and two of the slopes, because we have two variables now. We have two inputs. To consider the interaction, what we need to do, we can add one new theta, one new adjustable slope that we want, and the interaction between two variables, xi1 times xi2. The multiplication of these two by some parameter, hyperparameter, or slope value that we want to find for our regression model, we can consider interaction. Now it means that not only solely this effect on the output, but also the interaction between those two can be considered. Who finds proper parameter? Our learning model. We'll find out how much interaction is important, so that this parameter over here will consider it much more to train our model. Is it clear? So I think it should be very simple. If you have like even much more variables, then you should consider different interaction between all of those. So we say we have a note that it is recommended that if we include interaction in the model, we need to also include main effects that each independent variable also has. I can simply explain to you that whenever you think a little bit of interaction is there between two variables, it's highly suggested to put it there, because if it's even very low, then these theta parameter during learning procedure will find out a small effect and will be better than not considering it if there is any interaction between two variables. Unless you know certainly there is no interaction. Okay, so any questions so far? Now we want to say, we already briefly answered this, but let's have a look. We say most of the models that we draw here in this chapter were linear. But what if we want to consider nonlinear model? If our data is in a form that I cannot predict with one simple line. What we can do, we can bring nonlinearity. How we can do, let's first see the definitions. So, in linear regression models, we assume linear relationship between independent variables for simplicity to understand all the concepts. In nonlinear regression, we can compute more complex relationship between variables that is not linear, and we can call it as polynomial function. So when we call a polynomial function, we are not limited to one specific one. We can, for example, use exponential function. We can use logarithmic function. We can use power functions and different ones in order to predict nonlinear model. And a choice of a specific nonlinear function depends on the nature of data that we have. How it looks like, you've seen in first chapter a couple of times. So this is a model that is nonlinear, but we want to see how it can be shown in our model that we defined from beginning. What we need to do, so let's say we had two x's simply for advertisement on TV and social media. So we write the same term, theta hat 0 added by theta hat 1 x I1 and theta hat 2 x I1 to the power of 2 now. So that I'm adding second degree the same x I1, the variable that I have, with new theta hat parameter to the power of 2, so that it is quadratic model. I can continue this to how complex I want to the power of n. So that how much more I increase the complexity, this increases the complexity of model. For example, this is the sample that we've seen already. We have a couple of data. The predicting with the orange line you can see here is not good, of course. The error amount is too high. So we wanted to predict with one model that you can see in gray line here, and more complex model, the blue one, with increasing the degree. And you can see the degree here is 11. So it means that 11 times we increase these numbers here up to the power of the 11, so that here we have this model over there. Can we increase like to 50, 30? Yes, we can do. How much more make it complex? Then this line will try to follow all of these. But we said that that's overfitting. We don't want that to. So for example, for this data set, you can see that even the simple sign like model is very efficient to predict the model. And we also discussed now you know the metrics how to evaluate the performance of each one of this. So polynomial regression model with multiple predictor also can be written in this form. Here we had one predictor xi1 to the power of n. Here we can include multiple predictors. If you want to include that, what you do, each one of these terms should be separately inside how many degrees that you have. You can increase it. For xi1, you have many, depending on your definition, added by for xi2, second feature. For third feature, you can do the same. This is how you can bring a nonlinear model for multiple predictors or multiple independent variables. Is it clear? Any question? All right. So if you learned so far, it should be very easy. Just we added one intercept per each slope multiple degrees. So here we talked about nonlinear regression function. Now if we have multivariate multiple regression, what happens? First of all, what we call multivariate, the question is, again, so far, we discussed that, okay, we have a prediction, we have multiple x's, we discussed so far, but always we discussed about output, one output. What if we have two outputs? What if we have multiple outputs that we need to predict from same data? Can we formulate it? Can we show that? Of course, we can do. So how we can write it? Let's directly go to the formal equation. We can, how we were defining yi1, we can add index instead of yi, we can add yi1 so that we can write the same equation for one output. Second output, we can write another equation, but in the same form. So what's the difference? The difference is that now we want to find more parameters. So this is theta hat 0, 1, this is theta hat 0, 2. So that we have, again, 6 more parameters, for example, over here to find what are the best model for each one. So from same data, we can predict now 2 outputs. What's the problem here? There is a small issue. Not kind of problem, but something is missing still. No idea? Should be very simple. We said that between x's there can be interaction, right? And we learn how to include it. Between y's there can be interaction too, right? So if we want to make it more complex, we need to consider the interaction between the outputs between y2. So that I didn't write it here for you because mostly these equations working pretty fine. No need to make it more complex most of the time. But if in some cases you need it, you also need to consider interaction between 2 of the outputs, not only 2 of the features. Any question?
So this is not a multivariate multiple regression model?
Yeah, it is multivariate multiple regression.
It's not, or is it?
It is.
It is?
Yeah. Yeah, it is multivariate multiple regression. Because why we call it as multivariate? Because we have multiple outputs over here. Yeah. But before that, we were talking about multiple regression model that we introduced it already. Now I just extended to much more complex. So why we were not talking from the beginning on like these more complex models? Because to make everything simple, to understand metrics, to understand relationships, to easily understand the plots models, then we can now bring include all complexities. Then we have complex data, complex models, and do the prediction. And we know almost the most important elements that we need to consider to be ready to train some optimization algorithm to find these parameters that today we will discuss. Actually, only thing that is missing now is finding these thetas. How to find those. That today's course, in next chapter, we will discuss. At the end of this chapter, you have one assignment. You need to have, based on the codes that I already gave, and some today I will give you, you need to combine qualitative and quantitative with multivariate multiple approach that you need to calculate the p-value and t-statistic first, then interpret the results. Actually, you just need to bring more complex models into your model that you have. It should be very simple, like less than 1 hour work. Okay, in this chapter we discussed and understood the multiple linear regression models. Then we described the different feature selection models. We talked about the qualitative and quantitative independent variables, and we saw how interaction between independent variables are working. Then we discussed multivariate multiple regression and how we can solve complex, more complex data interaction between two games.